Pick any 4-digit number you like, as long as its digits are not all the same. Let us take 3524. Now do a very simple thing to it. Write its 4 digits in descending order, largest to smallest, to make the biggest number you can from them. Then write them in ascending order, smallest to largest for the smallest, and subtract the small one from the big one. For 3524, the biggest arrangement is 5432, the smallest is 2345, and the difference is 3087. That is one round. Now just do it again to the number you got, and again and again. It is the kind of pointless-looking arithmetic game you might doodle in a margin. Sort the digits, subtract, repeat. There is no obvious reason it should go anywhere in particular. And yet, if you keep turning this crank, something almost eerie happens. No matter which 4-digit number you started from, you very quickly get stuck on one specific value, and then you never leave it. That value is 6174. Let us watch our example fall the rest of the way. We were at 3087. Sort its digits and subtract 8730 minus 0378, and you get 8352. Do it once more, 8532 minus 2358, and out comes 6174. 3 rounds, starting from 3524, and we have arrived. And here is the thing that makes it a phenomenon rather than a fluke. It does not matter where you begin. Start from any 4-digit number with at least 2 different digits. Run this same sort and subtract crank, and you will always, without exception, be delivered to 6174. Every one of them ends in the same place. It is like a drain that the entire world of 4-digit numbers empties into. This behavior was noticed by an Indian schoolteacher named Kaprekar in 1949, and the number 6174 now carries his name. It is called Kaprekar's constant. The first question is the obvious one. What is so special about that particular number that everything gets caught on it? The reason everything sticks to 6174 is that 6174 sticks to itself. Run the routine on it and see. Its digits in descending order make 7641. In ascending order, they make 1467. Subtract the second from the first, 7641 minus 1467, and the answer is 6174 again. It reproduces itself exactly. Once you land on it, the very next step hands you back the same number, and the step after that, forever. In the language of these processes, it is a fixed point. An input the machine leaves completely unchanged. So 6174 is not just where things tend to go, it is a genuine trap. If the process ever produces it, and we are claiming it always eventually does, then it holds you there permanently. But being a trap that you cannot leave is only half the mystery. The other half is why every single starting number is guaranteed to fall into that trap, and to do it so astonishingly fast. Here is the part that turns a curiosity into something genuinely surprising. It is not just that you always reach 6174. It is how few steps it ever takes. From any legal starting number, you arrive in at most 7 rounds. Not a few dozen, not a few hundred. 7 at the very most, and usually fewer. To see the slowest possible descent, start from 1004, sort and subtract, and you get 4086, then 8172, then 7443, then 3996, then 6264, then 4176, and on the 7th step, 6174. Even this worst case, chosen to drag its feet as long as arithmetic allows, still lands in exactly 7. Think about what that means across all the numbers. There are 9,990 valid 4-digit starting points, an enormous varied crowd. Sort them by how many rounds they need, and every single one finishes within 7. Most take 3 or 5 or 6. A stubborn couple of thousand of them need the full 7. But not one number, anywhere in that whole range, ever needs an 8th. The entire infinite feeling supply is corralled into a fall of at most 7 steps. Picture the whole thing at once, as a map of where every number goes. Draw a dot for each 4-digit number, and from each dot draw a single arrow to the number the routine sends it to next. Because the process is completely deterministic, every dot has exactly one arrow leaving it. Follow the arrows from anywhere and you are walking a one-way path. What that map looks like is a vast river system. Thousands of little tributaries, the starting numbers that vanish after a single step, feed into larger streams, which feed into a handful of main channels, which all pour, within 7 steps, into one final basin. And sitting at the bottom of that basin, with its own arrow pointing right back at itself, is 6,174. There are no other basins, no separate little loops off to the side, no numbers that circle among themselves and never reach the drain. Compare that to what you might have expected. A random one-way map on 10,000 dots would normally have several loops, several dead ends, a whole messy delta of separate destinations. This one has a single destination, and everything on the map is upstream of it. For 4-digit numbers in our ordinary base 10, the entire map has exactly one sink, and it swallows everything. That is a remarkably orderly thing for such a crude little procedure to produce, and it is fair to ask why the sorting and subtracting should conspire so perfectly. The engine underneath is the subtraction, and there is real structure hiding in it. When you take a number, sort its digits big to small and small to large, and subtract, the answer depends only on the 4 digits you have, never on their original order. So the whole process really acts on the collection of digits, not the number itself, which instantly shrinks the problem. There are only so many ways to choose 4 digits, far fewer than 10,000, and the subtraction shuffles you among them in a fixed, traceable way. Work through which digit collections can follow which, and the arrows are forced. Every path is pushed, step by step, toward the one collection, 7641, whose big minus small difference is itself. There is no room for a second stable pattern to hide, and no room for an endless loop, because each subtraction strictly herds the digits toward that single arrangement. It is not magic then, so much as a rigid piece of bookkeeping about digits. But rigid bookkeeping is exactly what makes it feel magical from the outside. You throw in an arbitrary number, the machine ignores everything except which digits are present, grinds them through a forced sequence of subtractions, and spits you out at 6,174 every time. Which raises the natural question of what happens to the numbers we quietly excluded at the very start. We had one rule going in. The 4 digits must not all be identical. That exclusion is not a technicality. It is the only way to break the machine. Take a number whose digits are all the same, like 2222. Its largest arrangement is 2222, and so is its smallest, because there is only one arrangement. Subtract them and you get 0. The routine collapses instantly to nothing and stays there. The same happens for every repeated digit number, from 1111 up to 9999. They form their own trivial trap at 0, and they are the sole numbers that never reach 6,174. Every other 4-digit number, all 9,990 of them, flows to Kaprekar's constant. So there is exactly one escape hatch, and it is the boringest one imaginable. Use only a single digit, and you fall to 0 instead. Rule that out, and the constant is inescapable. It is a beautifully tidy dichotomy. Either your number is utterly uniform and dies at 0, or it has any variety at all and is swept in 7 steps or fewer into 6,174. Now the temptation is to think this is some deep universal law of arithmetic. It is not, and the quickest way to see that is to change the number of digits. Try the same routine with 3-digit numbers instead of 4. Sort the 3 digits down and up, subtract, repeat. It behaves just as beautifully, but it homes in on a different constant, 495. Check that 495 is its fixed point, descending 954, ascending 459, and 954 minus 459 is 495, itself again. And just like the 4-digit case, every valid 3-digit number reaches it fast, this time in at most 6 steps. So the phenomenon is real for 3 digits too. But the magic number is completely different. There is even a small family resemblance worth noticing. Both constants end in the digits that hint at their structure, and both arise the same way, as the one-digit collection whose descending minus ascending value equals itself. For 4 digits, that collection is 7, 6, 4, 1. For 3 digits, it is 9, 5, 4. Different digits, same idea, and the routine finds it either way. That difference is the tell. If this were a universal truth about sorting and subtracting, the same constant would appear regardless of length. Instead, each digit length has its own behavior, its own special number, or lack of one. 6174 is not a law of nature. It is a specific fact about 4 digits written in base 10. And for most other lengths, the tidy picture falls apart completely. Try it with just 2 digits. Run the sort and subtract crank, and you do not settle on any constant at all. Instead, you get trapped in a loop that cycles forever. 9 becomes 81, 81 becomes 63, 63 becomes 27, 27 becomes 45, and 45 takes you right back to 9, around and around with no fixed point anywhere in sight. 5-digit numbers are worse still. There is no single constant, and instead several different loops that numbers fall into depending on where they start. The clean, one-drain picture we found for 4 digits is actually the exception, not the rule. Most lengths give you cycles, or several attractors, or a tangle, which makes what happens at 4 digits genuinely lucky. Out of all the choices of digit length, it is one of the rare cases where every path, save the uniform digit numbers, funnels to a single point and does it within a tight 7 steps. Kaprekar did not discover a sweeping principle. He discovered a small, precise miracle that lives specifically at 4 digits in base 10 and nowhere obvious nearby. So step back and hold the whole picture. You take the crudest arithmetic imaginable, sorting 4 digits and subtracting, an operation with no memory and no cleverness in it. And out of that crudeness comes a perfect little machine with a single destination. Feed it any of nearly 10,000 numbers, and in at most 7 turns of the handle, it deposits every one of them on the exact same value, 6174, where they stay forever. The only survivors are the numbers too uniform to move, which fall to 0 instead. What makes it worth more than a party trick is the shape of the truth underneath. A completely deterministic process, run on a huge and varied set of inputs, can funnel all of them into one point, a single attractor that pulls the entire system in. That is the same idea that governs how complicated systems settle down all across mathematics and science, from the orbits of planets to the states of a cooling material. Kaprekar's constant is that grand idea in miniature, small enough to check by hand and strange enough to remember. A crude machine, an enormous crowd of inputs, and one number at the bottom that catches them all. This was the last in this run of the series. Thanks for watching, and stay for what comes next.